Oops. Try this again. Oh no, let's not do this. What? Here we are. Why is it doing this? Give me a moment while I fight this technology. I've never seen anything like this, ever. Let's just get rid of it. Let's just stop it. Start this. All right. There. And here. All right. And share. Program. This. And that. Okay, finally. All right, so I've returned your homework number 2 for the high school folks. I'm almost finished grading it, and I'll be sending that back this afternoon. So this Friday is the test, and on chapters 12 and 13. That practice set that I gave you is very valuable in preparing for the test, as well as, of course, as doing the homework. And the full solutions to that practice set, not just the final solutions, but the full solutions are posted on Blackboard. So on Friday then, in addition to the test, we have due the third homework assignment and the first take-home quiz. Okay? So what we're going to do today then is finish up this last section in chapter 13, and we'll see if we get any further than that for today. On Wednesday, we will spend the period entertaining any questions that you guys might have and doing some problems. Right? Okay. So this section here is on velocity and acceleration. So it's kind of an application section. This right? Okay. 13.4, velocity and acceleration. All right. So we started this last time, and so basically this is what we have here. We have a position vector. We'll call it R of t. And then the derivative of that gives us the velocity vector. R prime of t. And then the derivative of that again gives us the acceleration vector. R double prime of t. And then the velocity also, it has a speed component. So speed is the magnitude of the velocity vector. All right. And we did a problem where we started with the position vector. So last time we started with the position vector. And from that, we obtained the velocity vector, the speed, and the acceleration. So from that, we obtained the velocity vector, the speed, and also the acceleration vector. Okay. All right. Now what we're going to do this time is the opposite direction. We're basically going to be given the acceleration vector, given the initial position vector and the initial velocity vector, and we're going to go backwards by integrating in order to get the position vector. So here we're going to start with the acceleration vector, and we're going to go and obtain the position vector. Okay. All right. So let's get the facts here that we're given. We're given that the acceleration is given by 4t times I plus 6t times j plus 1 times k, or in other words, it's in angle brackets, it's 4t, 6t, and 1. All right. Now what we're also given is we're given that the initial position, and this means the position when time is equal to 0. So that's the position at time 0. So this is going to be r applied to 0 is equal to this vector 1, 0, 0. We're given that. And finally, we're given a initial velocity vector. And again, this is when time t is equal to 0, and we're told that v at 0 is equal to what? I minus j plus k, which is the same as 1 minus 1 and 1. Okay. All right, so we want to find the position vector. So we're going to then, first of all, use the fact that the derivative of the velocity vector is equal to the acceleration. All right, we're going to use that fact, and we're given the acceleration vector, which is equal to 4t, 6t, and 1. So what process do we need to do to try to solve for the velocity vector if we know its derivative? I think I heard a mumbling of antiderivative. Okay, so the velocity vector is going to be the antiderivative of our acceleration vector, and so all we do is do the antiderivative of the component part, so that we've got 4t, 6t, and 1, and we do that dt, and now this, remember, this is an indefinite integral, so we are going to have a general constant vector. just like we do when we take antiderivatives of single variables. So this is a general constant vector. So let's get the antiderivatives of the component parts. So 4t is going to be 2t squared. 6t is going to be 3t squared. And 1 is going to be t. And then that's plus that constant vector. Now, so we have this formula for the velocity. Now, we are given some information about the velocity. We're told that at time 0, the velocity is equal to this vector. So, we can then obtain what's a specific constant vector here. So what we do is set t equal to 0, and we can solve for the constant vector. Okay, so that v of 0 on the left side, we are told is 1 minus 1 and 1. So we put that over there on the left-hand side. And then we plug in t here for all of these components, but they're all going to be 0, 0, and 0. Plus our unknown general constant vector. And so therefore we find that the constant vector plus the 0 vector equals this vector. So therefore that constant vector is equal to 1, 1, and 1. So now I can get a specific formula now for the velocity vector because I have a specific constant vector. So I can now say that our velocity vector is what? 2t squared, 3t squared, t plus 1 minus 1 and 1. And now let me combine the components of this to get it into a single vector, and we can say the velocity vector is 2t squared plus 1, 3t squared minus 1, and t plus 1. All right. Okay, that's our velocity. Now, we then realize that the velocity is the change in position over time. So now we use the fact that the change in the derivative of our position vector, we know is equal to the velocity vector. All right? Change in position over time is equal to velocity. So therefore, I can solve for my position vector just like before with the velocity by getting the antiderivative. If I know what its derivative is, I can then get the antiderivative to find out what it is. Okay, everybody clear on that? We're going backwards. So this is going to be the antiderivative of the velocity vector. And then, of course, again, because it's an indefinite integral, we're going to have another general constant vector, and just for avoiding confusion, I'm going to call it plus d. All right? So let's plug in here for our antiderivative what we had already gotten for our velocity vector. So that's going to be integral sign of what? T squared plus 1, 3t squared minus 1, and t plus 1. dt plus another constant vector. All right, let's get the antiderivative. So our position vector is, what do we have here? 2t to the third over 3. So, let me put my angle bracket. 2/3 t to the third plus, and we got a 1 there, so that's plus t, comma. 3t to the second gives me t to the third as an antiderivative. Minus 1 gives me minus t. And then t plus 1 gives me 1/2 t squared plus t. And then again, that's plus my constant vector. So just doing a simple antiderivative of each component. All right, now again, we had gotten some information at the beginning that our initial position vector was 1, 0, 0. Okay, so we can solve for that general constant vector. Okay, so we're told that r at 0 was what? 1, 0, 0. And now I'm going to plug in, this is t is equal to 0. So here I get 0, 0, and 0 right there. Is that right? 1, 0, 0. Bum, bum, bum. Right. Okay, so that again is going to be 0 and 0 and 0 plus my unknown constant vector d, and so we can see from this that our d vector has to be 1, 0, 0. So we're ready to get down our final answer then for our position vector, okay? So therefore, answer, our position vector is, okay, 2/3 t to the third plus t, and I'm just going to go on and add the components of the d vector right now, so that's plus 1, comma, and then it's t to the third minus t, and then that's just plus 0, and then finally it's 1/2 t squared plus t, and again that's plus 0. So that's my answer then, just going backwards. Anybody have questions just about that? All right. Okay. Something that you're going to see in, at least I know in homework, is this kind of a problem, and I'm going to try to skip some of the finer computations for time purposes, but this is what the general problem is. We're at ground level and we're firing some kind of projectile at an angle. So let this be the y-axis and this be the x-axis. And so we've got something that's being fired at a certain speed at a certain angle. So this velocity, this right here at x equals 0, we can consider this our initial velocity vector. Okay, it's going off at an angle, and we're going to call the angle that's here from the ground alpha. All right? Now, this projectile then, it goes up, and then of course it goes back down again. And then it hits the ground at some point. Now, we're going to assume that the only external force that's working on this is gravity. We're not going to consider any air resistance. So therefore, the only force that we're considering that's operating on this is the downward gravity force, okay, which is in the vertical direction down. Now, this initial velocity vector, we can break it up into a horizontal component and into a vertical component, all right? So this velocity vector, this has a magnitude of absolute value of that is going to be the magnitude of that. So the horizontal component is going to be the magnitude or the speed, that is also the speed that this thing gets fired at, times the cosine of this angle. And that's going to be for the I vector, for the X vector. And then we have a vertical component, which is going to be the speed, which is the absolute value, times the sine of alpha, and this is going to be for the J vector, for the vertical. All right. Now, only thing working on this is the gravity. So what we can, first of all, we know that we have, from Newton, F is equal to m times the acceleration vector. All right. So therefore, and we're saying that the only force on this is the downward gravity force. So this is going to be, because it's going downward, we're going to say that this is working in the negative direction. Going up is positive, going down is negative direction. So therefore, minus, the only force on this is minus the mass of whatever this object is. The acceleration is the gravity constant, g, and this force is strictly a downward vertical force. So its vector component is j for the y component. Okay. All right. Now, this gravity constant, if we're working in meters per second, g is equal to 9.8 meters per second squared. All right. Okay. Now, notice here then we have an m here and an m here, a mass and a mass. This is an equation. I can divide both sides by the mass, and I end up getting that the acceleration of this thing is equal to minus 9.8 times the vector j, right? I'm going to end up coming up with the formula and or pretty close to coming up with it. We'll see how much detail I come up with. Okay, this is the acceleration of this projectile from gravity. All right, now we can get the velocity. We notice that the acceleration is the derivative of the velocity vector. So therefore, the velocity, just like in the very last example, the velocity at time t is going to be the antiderivative plus some general constant vector. So therefore, the antiderivative of minus 9.8 is minus 9.8 times t, and that's in the j vector direction, and then so plus our general constant. Okay. So this is our vector, our velocity function. And then what we can do then from this is say we have this. Let's just say at t equals 0, basically our vector is equal to v sub naught. Okay. Just call it v sub naught. We don't have any more information on it than that. So therefore, I can solve for c by plugging in 0 for t, and I get that v sub naught, or v at 0, is equal to 0 times j plus c. So therefore, my general constant is the vector v sub naught. Okay. All right. Now, so let me go and write this up again. So for constant here is v sub naught, we have this. We have v of t is equal to minus 9.8 t times the j vector plus now our constant vector is v sub naught. All right. What I'm going to do now is replace my v sub naught vector with what I had written way up here, where I decomposed it into its horizontal and vertical components. So let me go on and do that. So I have minus 9.8 t times the j vector plus, and I'm just going to write this stuff down, the magnitude of v naught cosine of alpha times the I vector plus the magnitude of v naught sine alpha times the j vector. I'm just replacing that with v naught. And now what I want to do then is combine this is with my j vector, this is with my j vector, so let's put it all together, and I get this, that my velocity vector is equal to, let's put the I vector first. So we have the speed, which is the magnitude of v naught times the cosine of alpha times the I vector, plus, and now combine the two j components, and I get, in parentheses, minus 9.8 t plus the magnitude of v naught, or the initial speed, times the sine of alpha, and that's all multiplying my j vector. Okay, all right. Okay. Now, what I want to now do is go one more step further. I've got the velocity vector, so let me get a position vector. So we know that the derivative of the position vector is equal to my velocity. So let me do an antiderivative again to get my position vector. It's going to be my antiderivative of my velocity. And again, it's going to be plus another general constant. And what I'm going to get here when I do my antiderivative of the velocity is that I get the following. For the I component, I get, let me put it in angle bracket notation. Here's my I. Speed times the cosine, there's no t. So if I'm going to do the antiderivative, all I do is tack on the t. So magnitude of v naught times the cosine of the angle times t. That's my I component. And then my j component, I do the antiderivative of my second. So here I do have the t minus 9.8 times t. So that antiderivative is minus 4.9 t squared. And then I have a second part here where I have, again, the magnitude of the v naught, sine of alpha, and then I have to tack on a t. And then this is plus my unknown constant vector. Now the thing is, so this is my position vector, but at time t equals 0, we're assuming that at time t equals 0, my position is 0, 0, 0. All right? So therefore, this, what we have here then is, okay, times, these all have t's in them, t, t, t. So, what I come up with is that my d vector is just 0, 0, and 0. So, when the dust settles then, this is the formula that I come up with. And this is the formula you'll be using for number 25 on the homework. Okay, so here we have position vector r of t is equal to the following: the magnitude of the initial velocity times the cosine of the angle times t, comma, minus 4.9 t squared, plus the magnitude of v naught, sine of alpha times t, angle bracket. This is your x component of the position, and this is your y component of the position. Okay, so this right here, as far as homework is concerned, I'm not going to be, trust me, on the exam, I'm not going to be requiring you to somehow reproduce this whole problem. But this is applicable for the homework. So let me do one example using this formula. It's sort of similar to the homework. So this is what we have. A gun is fired with a bullet speed of 150 meters per second, and it hits the, let's just say it hits the ground at 800 meters away. Okay. What you're asked to find with this is find the two possible angles it was fired at. Okay. So let's look here at our formula that we're going to be using. Okay. Now, it hits the ground at 800 meters away, so this is your x value, all right? And basically then, we're told that the initial speed of this thing is 150, so therefore the speed, initial speed, which is the V naught magnitude, is equal to 150. So therefore we've got let's look at our x component. So we have 150 times the cosine of this unknown angle times an unknown time period. This, as we know, is equal to 800. This is the x component. All right. Now we're going to be given another, can do another equation. When this thing hits the ground, what's the y component? 0, right. So the y component is 0. So let's use our second thing here. So we have minus 4.9t squared plus, now our speed we're given is 150, sine of the unknown angle times t, and that is going to be equal to 0 when it hits the ground. So these are the two equations that we end up working with right here. Okay. Let's see. Well, I guess there are a couple of different ways we can work this, because what we're trying to find is we're trying to solve for alpha. We're trying to solve for that initial angle. Okay. Ideas on what you might start with? Note from here, we can actually get what we don't know. See, two things we don't know. We don't know the time that's elapsed, and we don't know the angle. But this one here, we can use this one to get the time, the unknown time, in terms of the angle. All right, we can do that. Let's just notice there's a t in both of these that equals 0. So let's factor out a t from the left-hand side, and we have minus 4.9t plus 150 sine of alpha, close parentheses, and that's equal to 0. All right? Now, so we have something that's factored and equal to 0, so that means that's going to occur when either of the factors is equal to 0. Well, the first factor is just t. So obviously, at the initial point in time, the bullet is still on the ground, but that's not going to be when it hits the ground again. So we're not interested in that particular solution. What we are interested in is the second one. So we set minus 4.9t plus 150 sine of alpha. We set that equal to 0. And let's solve for t in this equation. And what we're going to get when we do that is that t is equal to 150 over 4.9 times the sine of alpha. Okay. Now we're going to take that value of t and go back to our first equation up here and plug it in. So plug into the first equation, and now we can solve for alpha. All right. So we take our first equation, which is 150, so let me rewrite it here. 150 cosine alpha times t is equal to 800. Okay, so let me plug in my value for t, so I get that 150 cosine of alpha times 150 over 4.9 times the sine of alpha, that equals 800. Just plugging it in. All right, now we're solving for alpha here. Now no longer, we don't have t anymore, so we can solve for alpha. So let's just isolate on the left side, cosine of alpha, sine of alpha, get all the numbers over on the other side. So that'll be 800 times 4.9 divided by 150 squared on the right side. Now, this thing right here on the left, there's a nice trig formula that I can use. What double angle formula, or let's say double angle formula involves the sine times the cosine? Jenna? Sine 2, in this case alpha, sine 2 alpha. So let me write the formula down. Sine of 2 alpha is equal to what? 2 times I remember it as sin cos, 2 times the sine of alpha times the cosine of alpha. All right? So therefore, this cosine of alpha, sine of alpha is equal to 1/2 times the sine of 2 alpha. Okay? And that's equal to, well, let me say what number we have over here, 0.17422. So let's multiply by 2. We get the sine of 2 alpha is approximately equal to 0.34844, which means that 2 alpha is approximately equal to then the sine inverse of 0.34844. All right? We okay with those steps? Now this actually gives us 2 angles. The arc sine or the sine inverse goes from, never mind that. Let's do this. Let's do it like this, because that's not going to work out. Let's figure out what the arc sine, just use our calculator and get this arc sine. This is approximately 20 degrees. Okay. Because remember, arc sine is from, from minus pi over 2 to pi over 2, right? A smart trig class, all students take calculus. Arc sine is from minus pi over 2 to pi over 2, right? So therefore, if we work that out on calculator, that's around 20 degrees. Now, the thing is, now let me go back to my other drawing. Can anybody tell me why this would, so we're having that so alpha then, so 2 times alpha could equal 20 degrees. All right, but a smart trig class, what other angle could 2 alpha equal in the second quadrant? 160, right. Sine is positive in the first quadrant, sine's also positive in the second quadrant. So if we just draw like this, 2 alpha can also equal, 180 minus 20, 160 degrees. Both of those angles will work. If we go way back here, up here, either of those angles will work. So therefore, we have 2 alphas approximately equal to 20, and 2 alphas approximately equal to 160. Divide by 2, the initial angles either approximately 10 degrees or approximately 80 degrees when they fired it. Right. Okay. That took a little bit too long. One last thing here in this section, and I have no time to go through the derivation of it. But what's important, and this is also for homework, and I think it's also in the take-home quiz. This last thing has to do with what's called two components of acceleration. One is along the unit tangent vector. The other one is along capital N vector, which is the unit normal vector. We can actually remember, acceleration is a vector. What we can do with this acceleration vector, and the book has a nice 2 pages of derivation, or a page and a half of derivation of this, is that we can basically write our acceleration vector as the sum of something times the unit tangent vector. So something, let me just put a squiggle there, times the unit tangent vector plus something times the unit normal vector. All right. Now what those somethings are after the page and a half is this. So here's the formula that you'll be using in homework and take-home quiz. The acceleration vector is equal to something that we call a sub t times the unit tangent vector plus something we call a sub capital N times the unit normal vector. And here's the formulas for these things. A sub t is equal to, and you guys will not have to be memorizing this, is r, the position vector, r prime, the derivative of that, dot with the second derivative of the position all over the magnitude of the tangent vector, r prime, and a sub n is equal to the magnitude of a cross product, cross r prime cross r double prime, all over, again, the magnitude of r prime of t. So for those problems in the homework and quiz, those are the two formulas that you'll need to use. So I just have one example with this, and that'll complete the time here. So, example, a particle moves with a position function or vector function, I guess, position vector function, r of t equal to angle bracket t squared, and t to the third power. So as t varies, that's our various positions of this particle. So what we are asked to find is find a sub t, and the name for this that you'll see is the tangential component, and a sub n, which is the normal component. All right, so we just used the formulas to get this. So if we look at the formulas here, what we have to get is the derivative of the position vector, the second derivative of the position vector, and then we have to get a cross product in that. So first of all, let's get the derivative of the position vector, which of course is that's a tangent vector. So that's going to be 2t, and 3t squared. And then let's get the second derivative. That's going to be 2 2, and 6t. All right. Let's see what we need here. In the a sub t, what we do is we get the dot product of those two, and we divide it by the magnitude of the r prime. So let me get the magnitude of the r prime while I'm at it. Okay, that's going to be the square root of the squares of those components. So that's going to be what? Square of this is 4t squared plus the square of that, 4t squared, plus the square of that. That's going to be 9t to the fourth. So when we combine, we get the square root of 8t squared plus 9t to the fourth. All right. And then let's get our dot product, r prime dot r double prime. Okay, dot product, we multiply together the components and add it up. So the dot product is what? 2t times 2, that's 4t, plus 2t times 2 is 4t, plus 3t squared times 6t, that's 18t to the third. Adding like components, I get 8t plus 18t to the third power. All right. So it's just a matter of plugging in stuff. So therefore, this tangential component is this dot product, which is 8t plus 18t to the third over the magnitude of the r prime. And the magnitude of the r prime is the square root of, let's put it this way, 9t to the fourth plus 8t squared. Just plugging it in. And finally, let's then do, and this can, by the way, this can be simplified a little bit. How can I simplify this? Yeah, I can take a t squared out of the a radical and simplify it. I won't put that down here, but I can do that. So a sub n then, now let's go back here. We're almost done here. For a sub n, the normal component, we have to do the cross product of r prime and r double prime. So let's figure that out. All right. So r prime cross r double prime, I, j, and k. Let's see, r prime is 2t, 2t, and 3t squared. R double prime is 2, 2, and 6t. Okay. All right, so we do our determinant. We cross out that first row and column. We're going to get what? 12t squared minus 6t squared. So that's going to give us 6t squared times the I component. And this is an error that a couple of folks did on the homework, so please listen up on this. For the second component, remember we have to start out with a minus and then let cross out the first row and second column, and we get 12t squared minus 6t squared. So that's going to be 6t squared, but we have a minus in front of it. So that's our j component. And, let's see, where is our k component then? Plus the k component, what's that going to come out to be? 4t minus 4t, so that's going to be a 0 times the k component. All right. So that's in angle, so just I'm a couple minutes over, this is 6t squared minus 6t squared and 0. And so we have to do the magnitude of this cross product. So therefore, a sub n is the magnitude of this divided by the magnitude of r prime. So this is going to come out to be 36t to the fourth plus 36t to the fourth, all over what we had gotten previously for the magnitude 9t to the square root of 9t to the fourth plus 8t squared. And of course, there's some minor simplifying that we can do with that. So just be prepared to be able to follow basically the formulas in order to get those two components, but you won't be having to memorize these for Friday. I can assure you of that. Okay, so see you on Wednesday. We just want to do some problems and to help get you guys ready.